Talking about insoluble ionic compounds in the context of gravimetric analysis gives us an opportunity to review how we deal with ionic compound solubility in water from a quantitative perspective using the concept of chemical equilibria and Le Chatelier's principle. So obviously, first and foremost, in order to do a gravimetric analysis, you need to be able to combine your analyte with another ion that will induce a precipitation reaction. So you need to have your analyte and another ion in combination form an insoluble ion pair that will precipitate out of solution. And you may remember there are a couple of different ways from general chemistry that we deal with predicting whether ionic compounds will be insoluble or soluble in water. And the first of those relates to the use of your solubility rules. I've attached a copy of the solubility rules that I usually use in my general chemistry class to this lecture. It may be more or less exhaustive than the solubility rules that you were handed in your general chemistry section, but remember that by Gen Chem 2 we were moving beyond the concept of solubility rules to talk about quantitatively how soluble was an ionic compound, because in reality all ionic compounds are technically soluble in water to some extent. It's just some of them are hardly soluble in water at all. And the reason for their solubility or insolubility is ultimately related to the attraction to the lattice energy between the cation and the anion. And the extent of their solubility is reflected in two measurements that are based on equilibrium calculations of ion concentrations when you have two ions that can form a precipitate. And so remember, from a lattice energy perspective or a general solubility rules perspective, the higher the charge on the ions involved and the smaller the ions involved, the less likely the ionic compound that they form is to be soluble in water. So if you have highly charged ions, and particularly if those highly charged ions are very small, they tend to form water insoluble ionic compounds. And that's really the basis for a lot of the specific solubility rules. The water soluble ionic compounds tend to be formed from ions with +1 charges that are relatively large. But from an equilibrium perspective, we can actually put a number on the solubility of an ionic compound. And we measure the solubility of an ionic compound quantitatively in water using two measurements. One is its molar solubility, which is calculated from the other measurement, which is referred to as the solubility product, or the KSP. So the KSP is an equilibrium constant expression related to a chemical reaction in which a precipitate redissolves into solution, forming the two ions it's composed of. So the way I've written, for instance, I've written a KSP related to the solubility of mercury 1 chloride. Now mercury 1 is a funny cation. It's a cation that's actually composed of two separate mercury atoms, each with a +1 charge. And the overall charge on mercury 1 is +2. So it's a diatomic ion with a +2 charge. The anion that precipitates along with it is chloride, and the chemical formula for mercury 1 chloride is Hg2Cl2 solid. All right, so if we write the equilibrium expression in this way, we've written it in the direction describing the precipitation reaction. The solubility product is an equilibrium constant expression that describes the reverse of this chemical reaction. And so as a result, because in this equilibrium constant expression, the pure solid mercury 1 chloride will not appear, the solubility product constant is simply the concentrations of the ions involved in the precipitate raised to their stoichiometric coefficient. So remember, if we're looking at the reverse of this reaction, which is what the KSP refers to, we do products over reactants. The mercury chloride doesn't appear because it's a pure solid. So here are our products, mercury 1 cation and chloride. So we have the concentration of mercury 1 cation times the concentration of chloride squared. So remember, in general, when you're writing an equilibrium constant expression, it's products over reactants. Every chemical species is raised to its stoichiometric power in the balanced chemical equation, and pure solids and pure liquids do not appear. All right, so what we can glean from solubility from this equilibrium constant expression is that the lower the KSP value is, the less the precipitate is going to release or reionize to form its component ions. Therefore, a smaller KSP tends to indicate a less soluble compound. From the KSP, we can also calculate the molar solubility, which for mercury 1 chloride is simply the molar concentration of mercury 1 cation in a saturated solution of mercury 1 chloride, where saturated means that enough of the mercury 1 chloride is in solution that no more of it can redissolve. Concentrations of all the ions are at equilibrium, and if you put more mercury chloride in the solution, it won't raise the concentrations of the mercury 1 and the chloride anions in solution. So how do we calculate the molar solubility? In general, the smaller the solubility product constant, the KSP, the less soluble the ionic compound is. But it can be hard to make a direct comparison about solubility because depending on the formula of the precipitate, you'll have different ions raised to different powers. And so the magnitude of the KSP doesn't always tell you something directly about the concentrations of the ions that make it up at equilibrium. Instead, we have to go back and actually calculate what the concentration of mercury 1 would be in a saturated solution of mercury 1 chloride in order to determine how soluble the precipitate is in water. As a spoiler alert, because the KSP is so small, the concentration of mercury 1 cation is still going to be very small at equilibrium. But we can explicitly calculate the molar solubility by making the following equilibrium argument. So we'd like to know what the equilibrium mercury 1 concentration is in a saturated aqueous solution of mercury 1 chloride. And we know from reference, there's a reference table of KSPs in the Harris textbook, and you can find pretty reliable places, pretty reliable tables of KSPs for most compounds with a quick Google search. Whenever I do an example like this, I'll always run back to the table in Harris to pull out the KSP. But the KSP for mercury 1 chloride is quite small. It's 1.2 times 10 to the negative 18th. If we write the chemical reaction that goes with that KSP says that in our saturated mercury 1 chloride solution, the precipitate, mercury 1 chloride, will redissolve or reionize to make 1 mole of mercury 1 cation and 2 moles of chloride. In order to relate the equilibrium concentrations of the ions to their KSP, we need to use an ice table. And so the assumption is we treat the initial conditions like the solid has just been dropped into a beaker of water and hasn't had time to redissolve. Because the mercury 1 chloride is a pure solid and doesn't appear in the KSP expression anywhere, we don't note any concentrations in the column below the solid. At the initial time, time 0, there is no concentration of mercury 1 and no concentration of chloride in the water above the precipitate because these ions have yet to dissolve. As the reaction proceeds towards equilibrium, all the mercury 1 plus and all the chloride are coming from the original precipitate. Therefore, the change in the mercury concentration we're going to call X, and the change in the chloride concentration we're going to call 2X, because 2 moles of chloride are released from the precipitate for every mole of mercury 1. At equilibrium, the equilibrium concentrations will be X and 2X. To find the concentration of mercury 1 at equilibrium, we plug these terms into the KSP expression, and we say that the KSP is equal to, as we know, the mercury concentration times the chloride concentration squared. So we take our terms for mercury, we take our terms for chloride, we plug them into the form of KSP. We see that the KSP is equal to X times 2X squared. And that is still equal to the quantity 1.2 times 10 to the negative 18th. What we're going to do is we're going to solve for X, where X is going to be the mercury 1 equilibrium concentration that we're looking for. And so we square the 2X, which gives us 4X squared. Make sure you watch that. You got to square the X, you got to square the 2. So 2X times 2X is 4X squared times X, 4X cubed is equal to 1.2 times 10 to the negative 18th, where X is the concentration of mercury that we're looking for. To solve this for X, we first, order of operations, divide the 1.2 times 10 to the negative 18th by 4. and then we take the cubed root of the whole thing. That will give us x. So x is equal to 1.2 times 10 to the negative 18th divided by 4. Cubed root of the whole thing will be your equilibrium mercury ion concentration. And it turns out, solving that expression, if I've done my work here right, the equilibrium mercury concentration would be 6.69 times 10 to the negative 7th molar. So remember that because we manipulate the reaction conditions in a gravimetric analysis, most of the time when we're answering questions about a gravimetric analysis, we can treat the precipitation reaction like it's irreversible, and we don't have to worry about equilibrium considerations. But when you're designing a gravimetric analysis and you're trying to understand how much of your analyte ion you might be leaving behind, if your precipitant concentration is such and such, you may have to come back and consider the equilibrium nature of solubility to make sure that you design your experiment well. So considering that, it won't be too long before we're back into equilibrium again. And since you have an equilibrium question on your homework number 1, I couldn't resist this opportunity to go back and give you guys a quick review through how equilibrium and solubility treatments go hand in hand when you're talking about ionic compounds. If you have any questions on this example, please don't hesitate to get in touch with me, and we can talk it through in a little more detail and answer any questions you might have.